In this chapter, we'll be going over acids, bases, and buffers, and we'll be going over their properties and how they interact with one another. So, we have two definitions of acids and bases, and they are very similar to one another. The first is an Arrhenius acid. And an Arrhenius acid is defined as being able to produce H plus ions in water. And so when it's in water, it's going to dissociate or break apart into ions. And one of those ions is going to be an acidic proton, an H plus ion. And so all it is just a proton. And so an Arrhenius acid is able to make protons when it's dissolved and dissociated into water. Some other properties of Arrhenius acids is they have a sour taste. They turn blue litmus paper red. And in addition to that, we have also red litmus paper. And so if it's reacts with red litmus paper, it stays red. And then it's also able to corrode some metals. So the important things to remember is that it creates acidic protons when it reacts with water. It keeps litmus paper red, and it's able to corrode metals. There are several different types of acids, and so with each different type of acid, there's different ways to have their names determined. And so if you have an acid with a nonmetal, so you have a hydrogen, an H with a nonmetal, you will begin the name with the prefix hydro, and then you end with the suffix IC, and then you put acid as the secondary name to it. So in this case, we have HCl, and so we have, we had that chlorine there, and so you have hydro in the beginning. Then you take off you only keep the root or first syllable of that non-metal, so the chlor. You drop off the rest of that name and add IC, acid. So HCl becomes hydrochloric acid. Um, if you have an acid with a hydrogen and have an oxygen containing polyatomic ion, so a polyatomic ion that has oxygen within it, then you could have several different polyatomic names, and just depends on what the original um, acid name would have become. So the ClO3 ion, the chlorate ion, and we didn't really go over too much of the naming of the polyatomics, but if you have an ATE ending on the polyatomic ion, then that ATE becomes the IC ending. So the chlorate, if you have an acid with chlorate, it'd be chloric acid. If you had an ITE ending in the as a suffix for your polyatomic ion, then that ITE becomes the OUS ending. So the chlorite ion becomes chlorous acid. And so that just changes depending on how many oxygens you have in the polyatomic ion. And so we're not going to go too much into detail on this. You just need to recognize acids and bases and their chemical formulas and see that their names are associated with their chemical formulas. One thing that you can see with their chemical formulas is that they largely have hydrogen in the beginning of their chemical formula. This is just a table showing a lot of the more prevalent and more common acids. and the name of those acids, the anions that are within those acids, and the names of those anions. So I would expect you to recognize some of the more popular ones like hydrochloric acid, hydrobromic acid, nitric acid, sulfuric acid, carbonic acid, phosphoric acid, and then at the bottom acetic acid. Those are probably the more popular ones that you'll probably become more associated with, and so you should recognize those. So here we're just having a little check to see if we can properly associate the correct chemical name to these chemical formulas. So we have HBr, so we have a hydrogen with a non-metal, the bromine non-metal. And so with that, going back to the previous slide, if you have a hydrogen with a non-metal, that the beginning of the name should start with hydro, and that the suffix should end with IC and acid. So letter C, hydrobromic acid, would be our correct answer. And the number 2, we have CO3. That's the carbonate anion. And so if it's carbonate, then we should change that ATE ending to IC acid. And so this one should be carbonic acid. And so that's one of the more popular ones you should recognize. And so number 3, that wouldn't be one I would expect you to be able to figure out. And so you shouldn't be too concerned over that, just largely because we're not concentrating on polyatomic. We didn't concentrate on polyatomic ions in the previous chapter. So here is just the answers for that. Number 1 and number 2, I would expect you to be able to recognize. Number 3, like I said, not so much. We also have bases, and so we have a definition for an Arrhenius base. And so an Arrhenius base is able to produce OH ions in water. And so you can see the chemical reaction on the bottom of the slide. You see NaOH. And so the main thing with Arrhenius bases is that they're going to contain that ion, that OH ion. And so that's one of the easy ways to recognize you have an Arrhenius base. Other properties of bases: they taste bitter or chalky, they feel soapy or slippery, they turn red litmus paper blue, and also we also have blue litmus paper, and so blue litmus paper would stay blue. And then if we use the phenolphthalein indicator, that would turn pink if you were to add base to it. And so phenolphthalein is a very popular and very often used indicator in determining if you have a base or not. And so the important ones here is the OH minus ion, the color of the litmus papers, and the phenolphthalein color. Some of the common bases are listed here. You can see that many of them have the OH ion, and so that's the hydroxide ion. And so their names typically contain the hydroxide name within the chemical name of the base. And so here we have metals. All these are metals with the hydroxide ion. And so we can, going back to our chemical name rules, we use the cation first, or the metals first, and we keep their full name. So sodium or potassium or barium, they all say the same. And since these are ionic bonds, we don't have to indicate how many of these hydroxide we have, so it's just going to be their metal name and then hydroxide. So sodium hydroxide, potassium hydroxide, barium hydroxide. And then in the last case, you see there the iron. Because iron is a transition metal, you also should indicate the oxidation number, or what charge the iron will have by using the Roman numerals. Here's a nice summary table that clearly shows the differences between the acids and bases. And so Arrhenius acids produce H plus and produce OH minus. And so we're going to talk about Bronsted-Lowry acids and bases in just a bit. But here, there's a slight difference in that Bronsted-Lowrys donate H pluses and accept H pluses. So Bronsted-Lowry is centered upon the H plus. They are both electrolytes in that they dissolve and dissociate into ions in water, and so they can carry electrical charges through the solution. Their taste and their feel, you don't really need to be too concerned about that as far as me asking you a question about that on a test or anything. The litmus paper colors is good to know. The phenolphthalein colors or lack of color is definitely good to know. And then neutralization. And so acids will neutralize bases and bases neutralize acids. And we'll talk about neutralizations later on in this presentation. So if we were to ask to identify each of these characteristics as an acid or base, A has a sour taste. That is indicative of an acid. If it produces OH minus in aqueous solution, so aqueous just means when it reacts with water, that is a characteristic of a base. Has a bitter taste, that would be a base. An electrolyte, they're both electrolytes, that would be acid and a base. And then produces H plus in aqueous solution. And so H plus production is an acid. And so we can see all of those here. So we mentioned Bronsted-Lowry acids and bases. So Bronsted-Lowry theory centers upon the H plus. And so Bronsted-Lowry acids donate an H plus. And so here, when it reacts with water, we see that the hydrochloric acid here, HCl, reacts with water. And so it donates its H, its proton, to the water. And so that H adds on to the water to make H3O plus. Remember that it donates an H plus. So you gain an H, but you also gain that plus charge. And then since it donates that H plus, what's left is the Cl minus. All right, because we had that minus left over from the H. The chlorine kept the electron and the proton lost its electron. The hydrogen lost its electron. So the main difference here between Arrhenius and Bronsted is that Arrhenius, you don't see where the hydrogen goes. And here in Bronsted-Lowry, you see that the proton goes to the water to make the hydronium H3O plus ion. So it's a very common ion to see when we discuss acids and bases, is that H3O plus. It's called hydronium, and you should remember that and recognize that. Bronsted-Lowry base, again, Bronsted-Lowry centers upon the H plus in the reaction. And so in Bronsted-Lowry theory, you don't necessarily have to have an OH minus in the chemical reaction, or I should say in the chemical formula of the base. One popular one to look at is ammonia, NH3. And so Bronsted-Lowry's definition of a base is that it accepts the proton. So here, when you have ammonia, NH3, reacting with water, NH3 is going to accept the H+, and it's going to accept it from the water. And so you're adding H+ to the base, or the ammonia. And so NH3 becomes NH4+. Then what's left over in the water is you lost an H+ in the water, and you're left with OH-. And so you still have the production of the hydroxide ion in the reaction with water, the OH-, being produced by the loss of H+ from the water. And so you can, we often look at conjugate acid-base pairs in a reaction with acids and bases. And so a conjugate acid-base pair relate to one another and by the loss and gain of a single H+. And so one will occur in the forward and one will occur in the reverse. So if you lose the H+ in the forward, you're gaining the H+ in the reverse, and vice versa. And so here you just in the reaction on the bottom is just a generic acid-base reaction, and they're differing by the addition and loss of an H+. And so you'll be asked to show which are the pairs, the conjugate ace pairs in a chemical reaction, and we'll do an example of that. So here we look at HF, or hydrofluoric acid. And so here we have, we'll look at the pairings, the conjugate acid-base pairs of HF. And so the conjugate acid-base pairs differ by one H+. And so the base 2, or the conjugate base 2 hydrofluoric acid, or HF, would be F-. If it's in water, reacting with water, then you also have water and its conjugate acid-base pair as the hydronium ion, or the H3O+. And so when you have hydrofluoric acid in water, you're going to the hydrofluoric acid is going to donate its H+. And so when it donates its H+, it's going to become F-. H2O, in this case, is going to act as a base. And so it's going to accept that H+ from the HF. And so you're going to add the H+ to H2O, and that's going to become H3O+. We can do the same thing looking at the ammonia. So ammonia is a base. And so by definition, it's going to accept an H+. And so when it accepts H+, it's going to become NH4+. And that's called the ammonium ion. And when it's in water, the water is going to act as an acid, and it's going to donate its H+ to the ammonia. And what's left over is its conjugate base, which is OH-. So if we look at the reaction on the bottom, we have the conjugate acid-base pair of NH3 and NH4+. They differ only by one H+, or one proton. We also have another conjugate acid-base pair of H2O and OH-. In this case, they are conjugate acid-base pairs. They only differ by one acidic proton, one H+. And so we have those relationships in this reaction. So in this check, we're are to in number one, write down the conjugate base of each of these acids, and then in number two, we write the conjugate acids to each of these bases. So if in number one, if we're looking for a conjugate base, then we should be losing one H plus in each of the three acids in A, B, and C. And so HBr's conjugate base would be Br minus. In B, H2S, its conjugate base would have one less acidic proton, and so its conjugate base would be HS minus. And then for letter C, carbonic acid, you would lose one H plus, and it would become HCO3 minus. So all of them are just losing one acidic proton. In number two, we're looking at trying to figure out the conjugate acid. So here we're going to be adding an H plus in A, B, and C. So NO2 minus would become HNO2. So that minus becomes neutralized or balanced out by the plus sign of the acidic proton. So it would be HNO2. Ammonia, NH3, if you add an H plus, becomes NH4 plus. And then OH minus, if you add an H plus, it becomes H2O. And so we can see those relationships here. So if you're looking for the conjugate base, you remove an H plus. If you're trying to find the conjugate acid, you add an H plus. And in this learning check, we're just trying to identify if these two pairings in all A through E are indeed conjugate acid-base pairs. And so if they are, they should only differ by one H plus. And so in A, we have HNO2 and NO2 minus, and indeed they do only differ by one H plus. So A would be a correct conjugate acid-base pairing. In B, we see that we have two H's in carbonic acid and then none in the carbonate ion. And so in this case, they would not be a conjugate acid-base pair because they differ by more than one acidic proton. In C, we have two completely different anions. So in C, we would not be a conjugate acid-base pair. In D, they do differ by only one H plus, so they are conjugate acid-base pairs. And E, they only differ by one H plus, so they are also the correct acid-base pairings. And so A, D, and E are the only correct pairings. For number one, it's asking us to figure out what the conjugate base of the HCO3 minus is. And so a conjugate base, you should be losing another acidic proton. So you should have one less H plus. And so the correct one for number one would be A. The conjugate acid of HCO3 minus, so here it's just going the opposite direction, so the conjugate acid, you should be adding an H plus, and so that would be the original carbonic acid, letter C. The conjugate base for H2O, so a base, you're going to, the conjugate base would have one less H plus, so that would be the OH minus hydroxide, A. And then the conjugate acid of H2O should have one more H plus, and so that would be the hydronium ion, letter C. And so that's what we see here. So remember, conjugate base, you're going to lose one H plus, and conjugate acid, you gain one H plus. So here we have an actual reaction with these acids and conjugate bases. And so here we just need to identify the two acid-base conjugate pairs in each of the chemical reactions. So here in number one, we have HI with water in equilibrium with the hydronium ion and the I- ion. And so remember, acid-base pairs only differ by one H plus. So in number one, it would be HI and I would be one conjugate acid-base pair, and H2O and H3O plus would be the second conjugate pairings. In two, we have the first acid-base pair would be HClO with ClO minus. And then we would have the H2O with the H3O plus. And so those would be the two conjugate pairs. And then the last one, number three, we have H3PO4, and its pair would be H2PO4 minus. And then the water H2O conjugate acid would be the H3O plus, or the hydronium. And so that's what we see here. So you can draw lines to show those relationships, or to maybe better help you recognize those acid-base pairs. But all these conjugate base pairs only differ by one H plus. And so now we're going to discuss strengths of acids and bases. So not all acids and bases have the same strength. They, there are different types. They have they're able to react in slightly different ways. In that some are able to completely dissociate, are strong electrolytes, and some are weaker electrolytes that are unable to completely dissociate. So strong acids are ones that can completely ionize or completely dissociate and completely react in an aqueous solution. And so in this case, we would use a single arrow in the chemical reaction. And so here we have hydrochloric acid reacting with water. Hydrochloric acid is a very strong acid, and so it would completely ionize in water. Whereas if we have a weak acid, they only partially dissociate. So they do not completely react. And so you'll have some of the remaining or the original acid still in solution. And so you can see that in this case that you the HCO3 minus does not completely react with water, and so you symbolize that by showing the double arrows in the chemical reaction, because there's an equilibrium met. There are 6 strong acids in solution. HCl is one of them. There's a nice list on page 376 in the text that shows the 6 main strong acids. We have HI, HBr, HClO4, HCl, H2SO4, and HNO3. And so those are the 6 strong acids, and you should remember those 6 strong acids. There's many weak acids. One common one is acetic acid, which is found in vinegar. And so in the case of weak acids, they do not completely dissociate. And so you'll have some of the original acid when it's in with water. So here you see that listing from that page in the text. And so stronger acids have weaker conjugate bases. So there's an inverse relationship there. So even though HI is the strongest acid, its conjugate base is very, very weak. And so that just means that I minus does not want to react with a proton to go back and make hydroiodic acid, because hydroiodic acid is a very strong acid. And so so just remember that there's an inverse relationship. So the stronger the acid, the weaker the conjugate base. And it's just the opposite. So we have many different weak acids, And so the weaker the acid is, the stronger the conjugate base is. And so you can see that relationship here. So again, it's an inverse relationship. So H2CO3 carbonic acid is not only a weak acid, but it's also a diprotic acid. So diprotic just means two acidic protons. Di is the prefix for two, protic, protons. So it has two acidic protons. So the H2CO3 will react with water and partially dissociate and make some hydronium and some HCO3 minus. And so that's it's in itself is a weak acid, and so you only make some HCO3 minus. That HCO3 minus is also a weak acid. And so that ion is also able to be in equilibrium with water and make some of the H3O plus. And so when it does that, it makes some CO3 2 minus. And so it has two acidic protons. It's able to lose two of those protons to the water. H2SO4, sulfuric acid, is a very strong acid and is also a diprotic acid. The H2SO4 is one of those six strong acids, and so it will completely dissociate with water in water and make the HSO4 minus ion. That HSO4 minus is a weak acid, and so that particular acid only partially dissociates, and so you're able to make some more hydronium from that sulfuric acid. But most of the acid or the hydronium H3O plus is made from the first reaction because that's the strong acid reaction. Then you only make a little bit more of the H3O plus from the second loss of the protons. We have not only have strong acids, but we also have strong bases, and so the strong bases are easily to recognize because they are formed when you have group 1 or group 2 metals with the hydroxide or OH groups. And so in these cases, they're going to completely dissociate in water. And so we see the list of six of those um, strong bases. And so in each of those cases, they will completely dissociate into their metal cation and the OH anions. Most bases are weak bases, and so they only slightly dissociate in water and form few ions. And so the example they use here is ammonia. Ammonia is a weak base, and when it reacts with water, it makes the NH4 plus or ammonium and the hydroxide ion. And since it's a weak base, you use the double arrow to show an equilibrium. Many of the household cleaning products in our homes contain bases, and so you can see here a lot of the different cleaning products that you may use and their respective active ingredient bases that are in there. And so many of them use weak bases, and with the exception of drain cleaner. Here we're asked to identify each of the following as a strong or weak acid or base, and so here you just want to kind of use your memory in trying to remember those six strong acids and six strong bases. If they're not on that list, then they're going to be weak acid or weak base. So here we have HBr in letter A, and so that's going to be one of those six strong acids. In B, we have HNO2, not to be confused with HNO3. So HNO2 is a weak acid. NaOH, Na is a group 1 metal, and that's with OH, so that's going to be a strong base. H2SO4 is another one of those 6 strong acids in sulfuric acid. And uh, copper 2 hydroxide in letter E is going to be a weak base. So it has the OH, that's how you can recognize it's a base, and it's not with a group 1 or group 2 metal, so it's going to be weak. And so that's what we see in these cases. Another property that we're going to discuss with acids and bases is their dissociation constants, and more specifically, we're talking about acid dissociation constants. And so we see the letter K in this case, and remember when we use this capital K, we discussed equilibrium constants, and so that's basically what the Ka, or acid dissociation constant, is. It's an equilibrium constant specific to an acid. And so in a weak acid, the rate of dissociation of the acid is equal to the rate of the association of the conjugate base. So it's you know, basically saying that you're in equilibrium. And so because we have rates in the forward equal to the rates of the reverse, it means that the reaction is in equilibrium. And so just don't be confused by that wording here. But when you have a weak acid, it's going to be in equilibrium with its conjugate base. And so when you have an equilibrium, you have an equilibrium constant. And so you can write out the equilibrium equation, an expression as we've done in the past, where you have products over reactants. And so the only thing that makes it different here is when you assume that value of 1 for the water, because water is a liquid, and for liquids and solids we use the number 1 for the in the equilibrium expression. When you go ahead and do that, you're left with the H3O plus times its conjugate base in the product side, or in the numerator, divided by the original acid in the denominator. And so here is basically just showing what the equilibrium expression is going to do is basically tell you how weak or strong your acid is. Is it a very, very weak acid, or is it a moderately strong weak acid? And so if it's able to dissociate more, it's going to have make more H3O plus and more A minus. And if it's able to do that, then you're going to have a larger Ka. If it's very, very weak, then you would not make very many products, and so you would have a very, very small Ka. And so when we look in this case of formic acid, we see that formic acid uh, can react with water to make the H3O plus and make that formate ion, the CHO2 minus. And so the expression for the Ka is the products in the numerator, so H3O plus concentration times the CHO2 minus concentration, divided by the concentration of HCHO2. And so we have, in the Ka expression, we already assume the value of 1 for H2O because it's liquid. And so that Ka for formic acid is 1.8 times 10 to the minus 4. And that's going to be always the case as long as we are at that particular temperature. So here we have a table describing some different characteristics of strong and weak acids. And so a strong acid, you completely ionize, you completely dissociate. So it's going to be completely toward the product side. Whereas weak acids, they are going to be leaning toward the reactant side. They do not dissociate very much, so they stay largely non-ionized or non-dissociated. And so strong acids have very, very large Ka's because you make a lot of products. Weak acids have a very, very small Ka because you don't make very many products. Um, the concentrations of H3O plus and A minus, they are going to be equal to the original concentration of the acid when after you're done with the reaction. Whereas you're going to have a very small percentage of the H3O plus and A minus in a weak acid. Strong acids have very weak conjugate bases, where weak acids have strong conjugate bases. Here is just a list of the different Ka values for some common acids. And so if you have a larger Ka value, those are going to be stronger acids. So in this list of weak acids, phosphoric acid is the strongest of these weak acids, whereas hydrogen phosphate has the smallest Ka. So they're in this list of weak acids, they are the weakest acid. So here we're going to write out the Ka for H2S. And so in this, we want to write out the equation for the dissociation of the hydrogen sulfide. And so when you do that, you should show that when H2S reacts with water, you're going to make the hydronium H3O plus because the H2S donates the proton to water. And so when the water accepts it, it becomes H3O plus. And so then what is left is HS minus. And so the Ka expression is products over reactants. So the two products are H3O plus times the H minus. And that is over the reactants. So the one reactant we have to be concerned with is the H2S. And because water is a liquid, we do not have to use it. And so the expression is shown here. If we were to do the same thing for hypochlorous acid, first we want to write out the balanced reaction with water. And so that's what we see in this first step. We see HClO plus water in equilibrium, and it makes the H3O plus. And what is left is the ClO, the chloride ion. And so then it's going to be products over reactants. So H3O plus times ClO minus divided by the HClO. So in this next section, we'll be discussing the ionization of water and how we can use the properties of the ionization of water relating to the acid-base chemistry. So in the ionization of water, when you have water essentially reacting with water, you do make H3O plus and OH minus. It is little, but there is a small amount of this being done in the solution of water. And so when you have this in this case, we have one water molecule that will act as an acid and one water molecule that will act as a base. And so one of those water molecules will accept a proton and then one will donate a proton. And so we call this equilibrium the ionization of water. And we have an equilibrium constant that's associated with that. And we call that equilibrium constant Kw, because the W is standing for water. And so Kw's expression is equal to the concentration of H3O plus times the concentration of OH minus. And this is a constant, and it is equal to 1 times 10 to the minus 14, because in a solution of water, it will always have a constant of pure water anyway. It will always have a concentration of 1 times 10 to the minus 7 molar of both H3O plus and OH minus. It's just one of the properties that pure water has. And so Kw is always equal to 1 times 10 to the minus 14. And so that's significant because we'll be using that constant value. And so you won't be asked to memorize that value, but you should recognize it and know how to use it. And we'll show how to use it in this section. So the impure water will have an equal amount of H3O plus and OH minus. And so we know that water is a neutral solution. All right, it's not acidic and it's not basic, it's neutral. And so that's because we have equal amounts of these two ions. They neutralize each other. When we add acid to pure water, we increase the amount of H3O plus. And so we have a larger amount of H3O plus than OH minus. It becomes off balance. The opposite is true as well. If we add base to pure water, we increase the amount of OH minus, the amount of H3O plus goes down. And so here we see that when we have an acidic solution, we have more H3O plus than OH minus. When we have a neutral solution, those two ions are equal. And then when we have a basic solution, we have more OH minus than H3O plus. So when the significance of this is that whenever you multiply the concentration of H3O plus and OH minus, you will get a value of 1 times 10 to the minus 14. You always get a value of Kw. And so in these cases here, we see that when we have a neutral solution, we have both values of 1 times 10 to the minus 7, and when we multiply those, we get 1 times 10 to the minus 14. When we have these two different acidic solutions, they will have their two respective OH minus concentrations, but when you multiply them, you still get the value of Kw. And the same goes with the basic solution. In the two basic solutions, you have two different values of H3O plus and OH minus, but when you multiply them, they all come out to 1 times 10 to the minus 14. And so we can use that relationship to be able to figure out the concentration of OH minus in a solution when you only have the value for H3O plus. So if you have a weak acid solution and you know how much H3O plus you have in solution, you can then calculate how much OH minus you have in solution. And vice versa. If you know OH minus concentration, then you can go back and calculate H3O plus in this solution by using the Kw, or the water dissociation constant. And so this seems like, why would we need to know this? But this is going to build up into the next section of how we're going to use this to be able to calculate pHs of acids and bases. So if we're trying to calculate the concentration of H3O plus in a solution that has a concentration of 5 times 10 to the minus 8 OH, we shown before that Kw is equal to H3O plus times OH minus. And that's always equal to 1 times 10 to the minus 14. So we can rearrange that equation to solve for the H3O plus concentration. And so what we would do is divide both sides by OH minus. And we know that the OH minus is 5 times 10 to the minus 8. And so we can plug that into our equation, and we get a concentration of for H3O plus to be 2 times 10 to the minus 7 molar. So here, if we have an example of lemon juice, and lemon juice has a concentration of H3O plus to be 2 times 10 to the minus 3 molar, what is the OH minus concentration? And so here again, in order to go from H3O plus to OH minus, we have to use Kw. And so what we want to first do, so we first write out the expression for Kw. Kw is equal to H3O plus concentration times OH minus concentration. That's always equal to 1 times 10 to the minus 14. And so since we're looking for the OH minus concentration, we want to divide both sides by H3O plus. And so we get the expression seen in step 2. And so since we know the concentration of H3O plus, we can plug that into our expression, and we can solve for the H3O plus of the OH minus concentration. And we see there, and we get choice C. And so now we're going to be discussing the pH scale. And so the pH scale, that scale that we largely use to see if something's acidic or not. And so we're going to use those some of that relationships that we saw in the last section in this part here, and be able to show why that we were doing that, show the relevance of our work. So the pH scale is used to measure the acidity of a solution. And the pH scale ranges from 0 to 14. And that represents the concentration of H3O plus. And we'll discuss how those number values relate to the H3O plus concentration. When you have a pH of 7, that means that the solution is neutral. So 7 is the middle point, 7 is neutral. All values less than 7 is for an acidic solution, and all values greater than 7 describes a basic solution. So here's just a picture representing some common items that you are familiar with, and their respective pHs. And so many of the citrus fruits have citric acid, and so those will be on the acidic side of the pH scale, and those have low pHs. We even have things like soda, which has carbonic acid, and phosphoric acid. Even milk is acidic, it has lactic acid. And then we discussed earlier that many of our household cleaning products have bases in them, and so we can see detergents and window cleaner and stuff like that, Drano. Those all are in the basic side, so greater than 7 pHs. So when we have acidic solutions, we have pH less than 7, and so that means that the H3O plus is greater than 10 to the minus 7 molar. Neutral solutions have a pH exactly of 7, and so it has an H3O plus concentration of 10 to the minus 7. And then for basic solutions, if we have a pH greater than 7, we have a H3O plus concentration less than 10 to the minus 7 molar. So we can use several different tools to help us measure pHs. And so the first one is a pH meter that can actually give us an accurate reading of pH. We can use different types of pH papers and test papers that turn different colors, or use a comparison chart to use to figure out the pHs using that paper. And we can use indicators that turn different colors based on their on the solution's pH. And so here we're just have to indicate whether these different characteristics belong to acid, base, or neutral solutions. And so A, we have HCl with a pH of 1.5. So first off, we see HCl, that's hydrochloric acid, so that should indicate an acid to begin with, but then we also see a pH that's less than 7, so that is also a property of acids. Pancreatic fluid that has a concentration of H3O plus of 1 times 10 to the minus 8, and that is smaller than 1 times 10 to the minus 7. And so if it's smaller than 1 times 10 to the minus 7, that must be a basic solution. Sprite, a soda product, has a pH of 3.0. That's a pH less than 7, so that means it's acidic. For letter D, if we have a pH exactly of 7, that is a neutral solution. E, if we have a OH minus concentration of 3 times 10 to the minus 7. So in this one, what we would have to do is then use that OH minus and use the KW as we had used in the previous section. So we would divide KW by the OH minus concentration of 3 times 10 to the minus 10 to figure out the concentration of H3O plus. And we would get a value that is less than, or I should say greater than 1 times 10 to the minus 7. So that would be an acid solution. And then F, we have an H3O plus concentration of 5 times 10 to the minus 12. That is less than 1 times 10 to the minus 7, and so that would be a basic solution. And so we see all of those written here. So to determine pH based on the H3O plus concentration, we must use this equation here. And so you don't have to memorize this equation. This would be given to you. But pH is equal to the negative log of the H3O plus concentration. So you just have to make sure you have the H3O plus concentration, plug it into the formula to solve for the pH. So if we have a solution that has an H3O plus concentration of 1 times 10 to the minus 4, the log of 1 times 10 to the minus 4 is negative 4. So the negative of negative 4 is equal to 4. So in this case, the pH would be equal to 4. Since we are using log scales, the number of significant figures to be reported is determined in a slightly different way. I'm not going to be a stickler on showing the exact number of significant figures, but if you do want to be exact, what you would have to do is that the number of place values in the concentration of H3O plus in the coefficient number, that will be equal to the number of decimal places you are allowed to report in your pH value. So in the top one here, we have H3O plus. We have one number place in the coefficient, so you're allowed to report 1 decimal. In the second one, we have 2 significant figures in the coefficient, so you're allowed to report 2 decimal places. In the third one, we have 2 significant figures in the coefficient, so you're allowed to report 2 decimal places. So if we were to calculate the pH of an aqueous solution, you need to use the H3O plus concentration. Then we can plug it into the log formula and then adjust the number based on the number of significant figures to be reported. So here we're up to a problem where we're trying to determine the pH of a solution that has a concentration of H3O plus of 1.7 times 10 to the minus 3 molar. So all you really have to do is just plug it into the formula that pH is equal to the negative log of H3O plus. The only thing you have to be cognizant of is to make sure you put in or enter in the 1.7 times 10 to the minus 3 correctly into your um, calculator. So you want to just practice that several times to make sure that you figure out how to do it. If you don't know how to do it, I can show you how to do it on a calculator in lab. So in this case, the pH is equal to the negative log of 1.7 times 10 to the minus 3. And so that gives a long, big number of 2.76955, so on and so forth. And so the last step is to figure out the number of significant figures you're allowed to report. And so since the coefficient has two significant figures, then your pH is allowed to have two decimal places in its final value, which would be 2.77. Here, a very similar question. What's the pH of coffee if the H3O plus concentration is 1 times 10 to the minus 5 molar? And so here again, you just have to basically plug it into the formula of pH is equal to the negative log of H3O plus. And so since the log function has a base value of 10, then we get a very nice round number here of 5. And so here, 1 times 10 to the minus 5 has 1 significant figure in its coefficient, and so then you're allowed to report one decimal place, and so that 5 becomes 5.0, which is choice C. Here's asking us to calculate the concentration of OH, calculate the pH if the OH minus concentration is 1 times 10 to the minus 3. So this is a little bit more involved in that if we want to calculate pH, we would need the H3O plus concentration. But here we only have OH minus. So here we need to go from OH minus and go to H3O plus. Then once we get H3O plus, we can calculate the pH. And so in order to go from OH minus to H3O plus, we need to use the KW value. And so first we need to figure out the KW value. We need to figure out the H3O plus concentration by using KW. So we divide KW by the OH minus concentration. And so we get an H3O plus of 1 times 10 to the minus 11. Once we have that, then we can plug it into the pH formula. pH is equal to the negative log of H3O plus, which is 1 times 10 to the minus 11. And so we get a value of 11. And so 1.0 has a value of, has two significant figures in the coefficient. And so then we're allowed to report two significant figures in the decimal places. And so we get choice C. So here's a table that just kind of shows the relationship between H3O plus, pH, and OH minus. And so if we have a low pH, we have a larger number of H3O plus and a very small number of OH minus. And then everything gets flipped around as you go up the pH scale and you get more basic. Here now we're going to look at going in the reverse. So in order we want to try to calculate H3O plus given the pH. And so what we're going to do is use the fact that pH or negative log has a base value of 10, and so then the H3O plus concentration is equal to 10 to raised to the power of the negative pH. And so first we want to just write out the negative value of pH. And so in this case we have a pH of 8.25, so the negative pH would be negative 8.25. And then we use that negative 8.25 as our exponent. And so 1 times 10 to the negative pH is equal to 1 times 10 to the minus 8.25, and we get a value of 5.6234 on lots of decimal places times 10 to the minus 9. And to report the correct number of significant figures, since the pH has 2 decimal places, then we're allowed to report 2 significant figures in the coefficient of our H3O plus concentration, and we get 5.6 times 10 to the minus 9. Here we'll do another example of trying to determine the H3O plus concentration given the pH of 11.2. So here we are just going to first write out the negative pH. So the negative pH is a negative 11.2. Then we're going to use that number as our exponent. And so we have H3O plus concentration is equal to 1 times 10 to the minus 11.2. And we get a value of 6.309574 times 10 to the minus 12. And so since the pH only has 1 decimal place, we're only allowed to report 1 significant figure in the coefficient of our H3O plus concentration. And so it is found to be 6 times 10 to the minus 12 molar. Now we'll look at reactions of acids and bases. And so the first one we'll look at is how acids react with metals. And so when an acid reacts with a metal, in general, you will form hydrogen gas and a metal salt. So the anion in the acid will react with the metal or combine with the metal, and then the hydrogen is given off as a gas. And so here we see that magnesium ribbon that we've used quite often in many of our labs, and that is reacting with the nitric acid and forms a hydrogen gas, so that's why it's bubbling up. And then you also form magnesium nitrate salt. When we have acids and carbonates, what we will produce here is we'll produce carbon dioxide gas, we'll produce water, and then an ionic compound or a salt. And so in these examples here, we have hydrochloric acid reacting with calcium carbonate or baking soda, the sodium bicarbonate on the bottom. And in both of these cases, they're forming carbon dioxide and they form water. And then they also form some type of salt. In the first case, it's calcium chloride. In the second, it's table salt, the sodium chloride. So here, just wants us to write out the products and balance the chemical equations given these reactions. And so in the first one, we have a metal reacting with an acid. And in the second two, we have carbonates reacting with acids. And so in A, like we said before, if we have a metal and an acid reacting, you're going to form hydrogen gas, and then you form the metals, the salts. And so you'll form H2 gas, and then zinc should have a positive 2 charge, and so you'll have zinc chloride being made as your salt. In B, you have magnesium carbonate and you have hydrochloric acid. And so you're going to have to form CO2, carbon dioxide, and you'll form H2O. And so then the salt that is left over is going to be magnesium chloride. Magnesium is a group 2 metal, and so should have a +2 charge, and you'll need 2 chlorines to balance that out. Um, and so then all you're left with is the balancing of the equation. In C, again, we have a carbonate and we have an acid, and so we're going to form carbon dioxide, we're going to form water, and then you're going to form the salt. And so in this case, you're going to have sodium bromide being made. And so you just have to make sure that you balance your equations properly. And so that's more review. The one reaction that we're going to be mainly concerned with is a neutralization reaction. So neutralization reactions is when you neutralize an acid and a base together. And so whenever you react an acid and a base together, you're going to form water and a salt. So the acid, by definition, is a proton donor. By definition, a base is a proton acceptor. So the base is going to accept the proton, accept the H+, and it's going to combine with the OH-. And so what an H+ plus an OH- is going to produce water. And then the resulting ions that are left over are going to form the salt. So Cl- is left over, and Na+ is left over, and those are going to react to make a salt. Sometimes we use the word net ionic equations, and so net ionic equations basically show and cancel out any ions that are found both in the reactants and product sides. And so in this case here, hydrochloric acid is a strong acid. And so you have H+ and Cl- in solution. You don't have HCl really, because it's such a strong acid that it's always going to be completely dissociated. So all that's going to be in solution is H+ and Cl-. The same goes with NaOH. NaOH is a strong base, and so in solution you only observe Na+ and OH- in solution. Salt, NaCl, is an ionic compound. It's a strong electrolyte. It's going to completely dissociate in solution. So when you have salt in solution, you don't have NaCl, you have Na+ and Cl-. And so when you write it out in that way, if you write out all the ions in solution, then you're going to rewrite the chemical equation as shown in the bullet there. You have H+ plus Cl-, you have plus Na+ and OH-, and that's going to make Na+ and Cl- and H2O. And then you just cancel out things that you see on both sides of the reaction. You basically cancel out like properties. So the Cl- are found on both sides of the reaction, and so those cancel out. The Na+ is found on both sides of the equation, so you cancel those out. And so that's why it's a net ionic equation. You're basically canceling out stuff that remains in solution, that doesn't make anything new. And so the only thing that's really being done in this formula or this equation is you're reacting an acidic proton with OH- to make water. So you're neutralizing the solution. And the last thing we'll talk about is buffers and properties of buffers and why buffers are important. So a buffer solution is a solution that helps maintain pH, and how it does that is it neutralizes any acid or base that is added to the solution. And so this is essential for our bodies because our bodies need to maintain a balance. Any small changes can really upset our systems. And so we need to maintain proper pHs because we have many reactions involving enzymes and proteins and such that are very specific to pH. And when their pH changes, then their shapes change, and then their reactions and their the way they work change, uh, and can be upsetting to our systems. Um, our blood contains buffers and helps maintain our blood systems to be close to about a pH of 7.4. Um, a change in our pH to our blood can disrupt many different uh, processes, including how well it can absorb oxygen and any metabolic processes. So when in a buffer, when you add an acid or a base, the pH is not going to change very much. You can look at the comparison to the water in this example here. If we have water that's a nice neutral pH of 7, if we add a little bit of acid, it can drastically change the pH to less than 7. Um, to down to, in this case, 4.0. If we add OH minus, if we add some base, it drastically changes it to 10.5. But if there was, instead of using water, if we use a buffer, we see there, in the bottom cases, that the pH changed only very slightly. And so it helps maintain that balance of toward the neutral pH. So buffers need to satisfy two main components to be considered a buffer. First of which is you want to contain an acid-base conjugate pair. And you also want these pairs to be of nearly equal concentrations. So if you have a buffer that has a weak acid, you want to have a salt that has its conjugate base in it, and you want to have those that acid and that salt of nearly equal concentrations. If you have a weak base in the buffer, you want to have a uh, salt that has its conjugate acid, and you want them to be very close in concentration. And the reason for this is that you want to have both acid and base present in the buffer solution. You want the acid there to react with any OH minus that is added to the solution, and you want a base to be present so it can react with any H3O plus or acidic protons in the solution. And so here we are asked if whether or not these considered buffers or not. You have HCl and KCl. HCl is a strong acid, so HCl will not be considered, will not be in any buffer solution. So A is not. In B, we have carbonic acid and we have sodium carbonate, or sodium bicarbonate. And in this case, we have a weak acid and its conjugate base. So yes, B is considered a buffer. In C, we have phosphoric acid and sodium chloride. This would not be considered a buffer because we don't have a conjugate pairing. We don't have any phosphate in the conjugate pair or the conjugate base. And then in D, we have acetic acid and we have potassium acetate. And so in this case, we have a weak acid and its conjugate base. And so that's what we see here. We see these explained in what was just discussed. So when we have a buffer, and in this case we have an acetic acid acetate buffer. When we have a buffer, we have two things occurring. We have the acid dissociation. We have the acetic acid in this case in equilibrium um, with its acetate ion, make an H3O plus And then we also have the salt. The salt's is a strong electrolyte. It's going to completely dissociate into its anion and cation. And so here we see that we're going to have both um, a lot of acid present from the acid dissociation. So weak acid, it's not going to completely dissociate. So we're going to have a lot of acid, um, of that weak acid in this case. And then we're going to have a lot of the anion, a lot of the um, acetate ion, because we have that from the salt. And so we have the conjugate, a lot of the conjugate acid and a lot of the conjugate base because of the properties of the weak acid and salt. And so the function of the weak acid is to neutralize any of the base that could be added to the solution. And so the if you add base, you're going to have OH minus present, and so that's going to react with the acetic acid, and that will be neutralized. The conjugate base is there to react with any acid, and so if you add any acid, like H3O, you're going to have H3O plus present. That's going to react with the acetate ion. And so these buffers have both something to react with the acid and something to react with the base to neutralize them and to prevent any large changes to the buffer solution. And so it's said to have buffer action occur because the weak acid neutralizes the base, and the conjugate base neutralizes any added acid. And so the pH of the solution is maintained.